Welcome back. In one of the earlier classes, I said there are two approaches to solve these problems. One was the shell balance approach that we saw in the previous class. Then this class we are going to see the conservation equation approach. The conservation equation that we have seen now is the continuity equation, the mass conservation equation, and we are going to apply it directly to get whatever we need. Let us, I'll tell you the reasons for doing that and so on and so forth. It's a much easier way of doing it, although it has some limitations. It could have some limitations. The shell balance approach is intuitive. It gives you a very nice feel of what's going on, a physical feel of what's going on. Understanding is clear. However, it's a little cumbersome. Okay. The continuity equation approach is overcomes that difficulty, and that's the reason why we are looking at this. As I said, the shell balances could become cumbersome for complex situations. Okay. Here it was, I took a simple case. It was cuboid, so nice and easy dimensions to work with, are intuitive from an intuitive point of view because we are used to that. Suppose your system becomes a cylinder, okay, and you'll have to do balances over a differential shell which is cylindrical in shape. Okay. Then things become a little more complex. You take a spherical system, you have spheres, let us say, and you take a spherical system, then you will have to do balances over a spherical shell. Okay, that can become even more. Let me say it would involve a lot more effort. It's not difficult, but it would involve a lot more effort. And for this reason, or it becomes cumbersome. So we look at this other approach, which is reasonably general, called the conservation equation approach. And of course, this you can just apply the equation, therefore it does not have that difficulty. Now, the visualization is a lot less in this. So let us first derive the continuity equation or the mass conservation equation for a species in a multi-species system. Okay. The earlier continuity equation that we derived was for what? You go back and check, pause the video here, go back and check and let me know. Why are we deriving the continuity equation again here? We have already done that. So what's the difference between this and that? Can you go back and check? Okay, if you checked, you would have found that this, the earlier one, was for a single species system or the total mass of a multi-component system. Here we are going to look at a species in a multi-species system. Okay. This will make it applicable more generally, and therefore we need to do this. And this is different from the earlier expression, and therefore we need to do this. The earlier continuity equation, this is nice to see many times. Therefore, I am just writing both forms. This is in terms of the derivative, the regular derivative, partial derivative, dou t of rho equals minus del dot rho v, and in terms of the substantial derivative, it is minus rho times del dot v. Nothing is constant here and so on. In other words, rho is not a constant here. Okay. This is the continuity equation that we have already seen. This is for a single component system or total mass. For now, we are looking at a species in a multi-component system. So let us consider a multi-component mixture flowing through a cuboidal element delta x, delta y, delta z, the same system as we saw earlier, fixed in space. Okay. So it was this. You have the x coordinate here, the y coordinate here, a right-handed coordinate system. Therefore, this is the z. And this is the cuboidal element of thickness delta x, delta y and delta z, and therefore, this point turns out to be x plus delta x, y plus delta y and z plus delta z here. Okay. So, this is our control volume or our system control volume, fixed volume in space, through which a multi-component mixture is flowing in 3 dimensions. enters in the x direction, it enters the phase at x, leaves at the phase at x plus delta x. Y direction, it enters at the phase at y, which is this, leaves at this at the phase at y is in this direction. So, it enters the phase at y, which is this, leaves at the phase y plus delta y, which is that, and in the z direction, it enters at the phase at z here and leaves at a phase located at z plus delta z, which is this. Okay. So, this is the mass conservation equation. dm dt equals, you have input rate plus minus output rate plus generation rate minus consumption rate. This is a single species, so you could have generation, you could have consumption through appropriate reactions that happen. Therefore, all the terms are relevant here. Earlier, if you recall, we did not consider generation and consumption because it was a single species, nothing else is going to happen to it, or it was a total mass. Even in the case of total mass, there is no generation or consumption, and therefore, we did not consider these two terms earlier. For a species I in a multi-component mixture, dou ai dou t, which is the mass of I with respect to t, this is mass. Mass is nothing but density times volume. So, density of I times the volume of the system is delta x, delta y and delta z. It is a cuboid, right. So, density times volume is mass, and we have written in terms of density and volume. N is, or Ni is a vector, and therefore, Ni is nothing but I Nix plus j Niy plus k Niz. So, Nix is the flux in the x direction, Niy is the flux in the y direction, Niz is the flux in the z direction, components of the total of the flux Ni, which happens to be a vector. So, input rate of I at x is nothing but the mass flux of I at x times the area, because we need mass rate. Flux times the area is the rate, and therefore, mass flux times the area. What is the area again? Just to recall, this is the x direction, this is the phase at which it enters, the phase area is nothing but delta y, delta z, and therefore, we have the flux times delta y, delta z. Similarly, the rate of the species I leaving the phase that is located, or that is being output at the phase located x plus delta x, is nothing but the flux of I at in the x direction at the phase located at x plus delta x times delta y, delta z. Okay. I hope you get the trend, the way of writing this. We are looking at mass per time, and we have fluxes, we multiplied by the rates, we have the various fluxes being written here. Can you write now a similar expression for the rate, input rate of I at y and the output rate of I at y plus delta y? Also do that for z. Okay. Pause the video here, write those, and then compare with whatever is being talked about. Go ahead, please. The flux of I, input flux of I, or sorry, the input rate of I at the phase located at y is Niy, the flux of I at y at the phase located at y. This is the y direction, this is the phase located at y, times the area. You know that the area is delta x, delta z, delta x, delta z. This is y direction. Similarly, the rate output from the phase located at y plus delta y is Niy in the y direction, the flux of I in the y direction, output from the phase located at y plus delta y times the same area delta x delta z. And hopefully you would have also gotten the z direction, which is the input rate of I at z in terms of the flux of I in the z direction at the face located at z times the area. The z area is delta x delta y, and similarly for output you have output rate of I at the face z plus delta z is the flux of I in the z direction at the face z plus delta x times delta x delta y. Okay. So, we have, what are we trying to do? We are trying to do a mass balance. We had input rate, output rate, generation rate, consumption rate. So, we have written the terms that will contribute to the input rate here, we have written the terms that will contribute to the output rate here. What is left over? Go back to the equation and find out. Yeah, the Rg minus Rc, we will consider that together here, net production rate. It is nothing but the reaction rate. The reaction rate is typically in terms of mole per volume per time. Therefore, mole per volume times the molecular mass, which will give you mass per volume per time, times the volume will give you mass per time. Okay. So, this we had done earlier, and we are doing the same thing here. We want every term in that mass balance equation here in terms of mass per time. Our measurements are in terms of other quantities, usual measurements are in terms of other quantities, moles per volume per time, and therefore, we are converting it into mass per time. So, this is the net production rate. Now, we put all these things, input, output, Rg minus Rc, into our mass balance equation, which happens to be this dm dt is Ri minus Ro plus Rg minus Rc, is what do you get? You get an expression, and if you divide throughout by the volume element delta x delta y delta z and take the limit as delta x tends to 0, delta y tends to 0, delta z tends to 0, you get this. Okay. We have seen the details already a couple of times. So, I am not letting you work through the details. If you want, you can do that. To feel comfortable, you could do this. You can of course see here, you have these various things, input minus output, then you put that into that expression, divide throughout by delta x delta y delta z, and so the terms that remain will form the expression for the derivative when the limit is taken, and so on and so forth, as we saw earlier. And therefore, the mass balance equation would become dou rho I dou t plus dou nix dou x plus dou niy dou y plus dou niz dou z equals Ri, the volumetric basis rate, times the molecular mass of I. We will call this equation 2.3.2-1. Vectorially, vector notation helps us write things in a compact fashion. We can write this as dou rho I dou t. This is nothing but, you could recall, del dot ni. Okay, you could write down the individual terms, take the dot product and see that it is actually reducing down to this, equals Ri times W, molecular mass of I. Equation 2.3.2-2. Now, if we divide throughout by the molecular mass, we get dou Ci dou t plus density divided by the molecular mass. Density is mass per volume. So, mass by molecular mass will turn out to be moles per volume. Moles per volume is concentration. So, dou Ci dou t plus del dot, this is mass flux divided by the molecular mass is mole flux, and therefore, capital Ni equals the molecular mass goes out here, just Ri here. Okay. So, this is equation 2.3.2-3. Now, let us begin with this dou rho I dou t plus del dot Ni equals Ri times the molecular mass of I, 2.3.2-2. We have already seen that this expression, okay, in a few classes earlier, minus rho di del Wi equals Ni minus Wint, reasonably general expression. Substituting Ni from this, Ni is nothing but Wint minus rho dou I del Wi. This, if you substitute here, we are going to get, what are you going to get? Why don't you substitute and tell me? Yeah, it's a good thing to do it interactively. You'll pick up much more. Pause the video here, go back, do this, substitute for Ni from this expression onto this expression, tell me what you get. Go ahead, please. Hopefully you got dou rho I dou t plus del of Wint minus rho dou I del of Wi, that is the expression for Ni from this, equals Ri molecular mass of I. We will call this 2.3.2-4, and by definition Nt is nothing but rho v, right? That's flux is nothing but density times velocity. That's what we saw in the very beginning. Therefore, Wint, this term, is Wi times rho v, and Wi is the mass fraction, rho is the total density. Therefore, total density times mass fraction is the density of I. So, this becomes rho I times v, and therefore, this equation can be written as dou rho I dou t plus del dot of rho I v minus rho di del of Wi equals Ri times the molecular mass of I. Okay. Let us call this equation 2.3.2-5. We are doing all this to set things up. So, it's nice the way it is falling into place. We are deriving the equation, the continuity equation that can be directly applied to solve problems. So, we are trying to do it as generally as possible, so that this would be applicable to a wide variety of situations. If you reorder this equation, take the various terms, you know this, right? This is del dot rho I times v. Rho I is not a constant here, and therefore, this is product of two functions. So, we are taking the derivative in 3 dimensions, and therefore, it is first function derivative of the second function plus second function derivative of the first function and so on will turn out here, and therefore, we get, okay, that's the next step. I've just split it up here, dou rho I dou t plus del dot rho I v minus del dot rho di del Wi. I have just taken the derivative explicitly. These were together earlier. I have separated out the terms, equals Ri mi, molecular mass of I. And here you could write this as dou rho I dou t times, I have taken rho times Wi as rho I. So, del of rho I this becomes, and now I am expanding. This is the product of two functions, as I mentioned earlier. Therefore, derivative would be first function rho I times the derivative of the second function plus the second function v times the derivative of the first function. Okay, I have essentially split this up. The rest remain the same. And now, if we impose the conditions, till here it is very general, we didn't assume anything. Now, if we impose the condition that the total density and the diffusivity of I are constants, which is applicable in a wide variety of cases. If the density is a constant, then we know that the equation of continuity reduces to del dot v equals 0, right? This we have already seen. So, if rho and di are constants, this term will drop out, del dot v equals 0. Therefore, this equation reduces to, under these conditions, now we have conditions, rho di are constants, dou rho I dou t plus v dot del rho I minus di is a constant and del dot del is del squared, dou dou squared dou x squared plus dou squared dou y squared plus dou squared dou z squared. If you are uncomfortable with it, just go and check the appendix in the book. It would give you how those things come about. Equals Ri times molecular mass of I. Equation 2.3.2-9. And now if we divide throughout by the molecular mass, we get the density divided by the molecular mass concentration, again density concentration, and this should go out. This should not be a part of this. Let's get rid of this right here. Okay, I'll take care of this a little later. Okay. So, we are dividing by the molecular mass, so that should not be there. And this equation 2.3.2-10, okay, let me go to the full screen mode. This equation can be used to get concentration profiles, and that turns out to be very useful, as you will realize as we go through the various examples and you work out the various exercises. Okay. So, this equation is applicable if the density and the diffusivity are constants. This equation is applicable in general. Okay. So, remember this. Here, of course, the V is the fluid velocity. So, here I have a set of tables which give you first in the equation of continuity for a species I in a multi-component mixture in general terms, and when C and Di are constant or rho and Di are constant, both are the same, and C and Di are constant, it reduces to this, easier to use in many different situations. So, the general case is AI, which is a little difficult to use because it is in terms of the molar fluxes, difficult to measure, whereas here this is in terms of C and diffusivity and velocities, which are much easier to measure. Okay. So, that is what this table consists of. First for rectangular coordinates, then cylindrical coordinates, conversion has happened, non-trivial conversion has happened from rectangular to cylindrical, and then in spherical coordinates. And as mentioned earlier, I would like you to make a copy, either a hard copy or a soft copy of table 2.3.2-1, which is in these three tables consisting of equations A1, A2, B1, B2 and C1, C2, okay, and keep it aside at a place where you can easily refer to. We are going to use these equations very often. Okay. Now, let us solve the same problem that we did using shell balances earlier. We had, remember shell balances, we had written a representative shell, or we had considered a representative shell, we had written our material balances over the representative shell and come up with useful expressions. Earlier, the problem that we just did with the shell balance method was the diffusion of species I through a membrane, which again has various applications. It could be a cell membrane, it could be various other membranes that we use in biological engineering. So, whatever we did using shell balances, let us do using the conservation equation. You will see that it happens in one step. So, we will consider the Cartesian coordinate system, because this happens to be the system that best fits the geometry of the membrane. And let us choose that equation and cancel the terms that are not applicable. In this case, if we consider C or rho and D to be constants, then we could use equation B from table 2.3.2-1, which is this. Yeah, I think it's A2, not B. B turns out to be this, so I need to convert it to A2. So we are going to choose equation A2 from here because it is rectangular coordinates which fits the geometry. C and D are constants, therefore this equation can directly be used, which is much easier to use. Okay. So this is the equation here, dou Ci dou T, and this is the velocity times the concentration gradient, and this is the second order term here and the reaction rate term here. Now you see how easy it becomes. It is steady state and therefore the time derivatives are set to 0. There is no convective or the stirring bulk motion, and only in the case of bulk motion will these velocities come into being. Therefore, we can cancel this. There is no velocity component in the x direction, there is no velocity component in the y direction, there is no bulk velocity component in the z direction. There is no equivalent of the whole liquid moving. It is only the species that is moving in the liquid. That movement is taken care of in the diffusive terms, and there is no bulk motion here. The liquid is stationary or the system is stationary, right. So all these terms go to 0, and here again the motion is only in the x direction, therefore there is no movement in the y direction because the concentration does not vary with y. Y is in this direction, the concentration does not vary with y. Here again it is equal to 0 because the concentration is not a function in the z direction, and there is no reaction that is taking place, therefore this goes to 0. So in one single swell step, just by taking the comprehensive equation, cutting out the various terms that are not applicable, you don't have to remember this, you just write down from the table, and in one step we got this equation that we derived through shell balance over various different steps in the previous case. So that is the ease of working with this, although there are some caution that you need to exercise here while using this. So we got this equation, which is the same equation that we got earlier through shell balances. Di dou squared Ci dou x squared equals 0. Now we come to the caution. Shell balances, although generally applicable, can sometimes become cumbersome, and thus this conservation equation approach would be convenient to use in many situations. That is the reason why we got into this. However, note that we derived these conservation equations based on standard shells, cuboidal shells, cylindrical shells, spherical shells. Okay. If the shell shape happens to be different, okay, for example, if we have a cone, okay, the cone, there is a gradual change in the cross sectional area and so on and so forth. There could be various situations where the area changes. For example, if the cross sectional area is variable, equation A2, B2, C2 are not applicable. You know that those constants C, DAB, we derived by taking the area to be a constant. If you go back and check, we would have implicitly assumed that the area doesn't vary, therefore we cancel the areas. And if that is not applicable, those equations will not be applicable. Okay, so be very careful whenever you deal with variable area. You cannot use A2, B2, C2. You can use A1, B1, C1. They are not based on area. Okay, that's what is mentioned here. However, verify that A1, B1 and C1, you are asked to verify that, are not affected by this aspect and are generally applicable. Go back, check this, convince yourself that this is indeed the case, or understand that this is indeed the case. If you are not able to understand, get back to me. I will talk to you on a one-on-one basis through email. Okay. That is what we have here. We had derived the conservation, or we have shown the conservation equation approach to solve problems, to get concentration profiles, which are important in many cases. To do that, we first derived the continuity equation for a single species in a multi-component mixture to make it generally applicable. That is what we did in this class. Let's stop here. We'll continue in the next class. See you then.